Welcome to the Week 3 lecture for microprocessors and robotics. This week we're going to get into programming a little bit. So first we're going to look at different programming languages. We're going to be especially focused on machine language, assembly language, and C language, getting a good idea of each of those. And then we'll look closer at assembly language. We're going to talk about registers and memory. We talked about those in the last lecture, but now we're going to look at how those play into programming. And we're also going to take a look at some of the basic commands that you'll be using when you're programming in assembly language. And we'll also see how the logic gates that we discussed in the previous lecture are also used or can be used in assembly programs. After all of the lecture material, we will look at setting up Code Composer and we'll review Lab 1. So our first question may or may not be obvious, but it is, what is a program? A program is getting the numbers and architecture to do things. We've learned about the binary and hexadecimal number systems, and we've reviewed some architecture of microprocessors and microcontrollers, but to make all of this work, we need instructions. And you'll find that every computer has a specific instruction set, and different computing systems require different formats of instructions. So we'll take a look at the different formats that instructions can be in, otherwise known as programming languages. Here's a simple list of programming languages, and they're in order from most complex to least complex. So one of the most complex programming languages that we'll briefly cover in this course is MATLAB. And this is especially used when you're performing a lot of mathematical functions. This is a great programming language to use for that. Perl and Python are also a little more complex programming languages, although not necessarily difficult to use. So just because a language is more complex does not always mean that it's more difficult. Python, you'll see it emphasizes code readability. So because the code is very readable, that makes Python very easy to use. Java is designed to run securely on any computer. It's kind of in the middle there, along with C. And later in this course, we'll be learning how to program our microcontrollers using C language. And you'll see that it's designed for flexibility and overall system access. Next, we have assembly language, and that's what we'll be covering this week as well as next week. This is human-readable machine language, so it can be a little bit harder to work with, but it shouldn't be too bad. And then at the very base level, we have machine language, which uses binary representation. And we'll take a look at what that means in a second, a little more in depth, but essentially we're using our binary numbers to code at the most basic level, and that is machine language. Throughout this course, I'll be using a couple different types of terminologies. We'll be talking about programming languages like we just did. We just talked about a bunch of different programming languages, and we'll also be talking about the computer architectures. So I want to very clearly define these two and how they work together. So we just saw languages. These are what we use to communicate with our architecture, right? They're how we send commands to the microcontroller or microprocessor. And then we also have our computer architecture. So this could be the physical components, the different components, essentially that make up your microcontroller. This is the architecture. This is how it's built and the specific components that go into it. And when you think about different components, it can vary based on type, right? So if you go to the store, there's different brands of cereal, right? There's all different kinds of cereal and there's different brands of cereal. So as funny as that kind of comparison is, apply that to computer architecture too. There's a variety of architectures, there's different brands of architectures, and so that's where we get our variety. And a complete system happens when we take our programming language and we use it with a specific computer architecture, and we combine the two and we have a unique system. So there are a lot of unique systems and unique combinations of these. We can have a set number of programming languages, a set number of components, but then when we combine everything, we can end up with, like I said, unique systems. And so a comparison for this that I like to use to help clarify this a little bit more is think about it like this second set of bubbles here. So the programming language, compare this to an actual language that people would speak. For instance, English. Think of the computer architecture as a country. So the architecture kind of acts as a modifier for the programming language. So you'll see as we go through some of these slides that assembly language is a standard language. If you learn one kind of assembly, you can probably use it on anything. But the specific commands will sometimes vary, or the setup will vary ever so slightly depending on which microcontroller that you use, which computer architecture you have. So the architecture acts as a bit of a modifier of the language, much as a country could act as a modifier of a language that we would speak. So for instance, English in the United States, an English speaker from the US is probably going to sound different from an English speaker in the United Kingdom, right? Both people are speaking English, but they'll probably sound very different. And so what happens in terms of a language is that we would call what each of these people have is a dialect. So a dialect is a unique combination of a language with that country. The country kind of acts as a modifier. It gives somebody a little bit of an accent. And the same thing happens where the computer architecture acts as a modifier of the programming language and gives us a complete system. Just a second ago, I mentioned that machine language uses binary numbers as part of its coding. And here I've just included a quick list. You don't have to memorize this, but it gives you an idea of what we have to do to get a letter in machine language. So for instance, if I wanted to code the letter R, if I needed that to appear, I would have to enter this binary sequence. And we have what's called an ASCII code. And it's simply the codes that it gives you a binary number that represents a specific character. So we can tie those number sequences to specific characters when we're coding in machine language. Luckily in this course, we do not have to code in machine language because it is made entirely up of binary numbers of those ones and zeros. So you'll see below I've given us a 4-line program fragment, just a bunch of ones and zeros. You can imagine to code this, it'd be very hard to keep those numbers straight. I'm sure even as you were converting numbers in the previous 2 weeks and adding those together, you may have found it a little bit difficult to keep all the ones and zeros straightened out. Most of you did well with that, which was great, but if you're staring at this kind of code all day, it can certainly get old and tiring very fast. And even this 4-line program fragment, it only means this equation. This fragment right here simply represents z equals x plus y. So you can imagine if you had to write an entire program using machine language, it would take a very long time and it would be very tedious. So if machine language is so tedious, why on earth would we use it? Well, there's a couple pros and you'll see a little bit longer list of cons. So some of the pros for using machine language is that since the language is already in ones and zeros, the CPU can directly execute the code. There's no translation, so to speak, of that programming. It's already executable. It's in that 1 and 0 form. And because of this, machine language leads to faster execution time. So it's directly executed, and that means it's much faster. The cons to this, though, if you'll remember that character chart just a second ago, is that when you're programming in machine language, that means you're going to have to become very familiar and essentially remember the equivalent binary values for every command, every character, and things like that. So this makes machine language very difficult to write, which means it takes forever to write. It takes a very, very long time to get in all those ones and zeros. And it also means that if you have any errors in your code, or rather when you have errors in your code, it's very difficult to find these errors and to correct them because you're just staring at a screen of ones and zeros. So we won't be using machine language in this course. We'll actually be using assembly language, which is a step up. So it's a little bit simpler, or rather it's much simpler to use than machine language. So here's a snippet of assembly language, and as I was saying, assembly language is much easier for humans to write. We're not trying to remember as many ones and zeros equivalents for things, or we don't have to use binary at all when we program in assembly language. But this means that it does require translation for the system to execute. And in this snippet, we can kind of see it's not immediate what this code means, but we can probably figure it out if we take a look at it. So right here, INCR, this probably means increment. So we're probably adding 1 to a value. Down here we have the jump command. This is telling the program to jump back to the top, which would be over here. And so these commands that we use in assembly language are a little bit more recognizable, and that makes it easier to remember the commands and easier to program the commands. And it also makes debugging easier because it's easier to separate out everything in your mind and in the space, and you can kind of tell where a mistake may be. It can be a little bit more obvious than staring at a screen full of ones and zeros. However, as I said, because assembly language is not written in ones and zeros, it has to be translated for the system to understand it. So assembly is easier for us as humans to write and to read and interpret, but the processing system still needs it to be in ones and zeros. So we use what's called an assembler, and this assembler turns the assembly language code into machine code for us. So it saves us a step, and it can save us a lot of time because we're not writing in machine code. We just have to use an assembler almost as a translator, or it is a translator, to get the assembly language into a format that the processing system can read. So here again is a pro and cons list, this time for assembly language, and you can see that the pros list is looking a little bit better for this one than it did for machine language. So in assembly language, as we saw, the commands are a little bit closer to English. Not everything is written out necessarily as an English word, but it's usually some sort of abbreviation or some sort of combination of letters that helps the brain recognize what that command is doing. Assembly language is also easier to remember because those commands are closer to the English language. That makes them easier to remember, so it's easier to write them, and it's easier to separate out those commands for the debugging process. And in turn, this is kind of a chain of events here, as you'll see, because it's easier to find the errors. You're also going to be less prone to errors because it's easier to keep things separate, and it's easier to find errors when they do occur. There's still a couple cons to assembly language. Because of that assembler that we just talked about, that means it's slightly slower to execute. Not significantly, but a little bit, because there is that middle step, that translation from assembly language to machine code for the processing system to be able to read it. It can also be difficult to modify assembly language without affecting the entire program. Hopefully you don't run into this. Our programming codes that we'll be using are fairly simple, but if you are writing a really complex code with assembly language and you found yourself needing to change something, it may not be a straightforward process. You may have to go in and change many, many pieces of that program. So that's certainly a drawback to assembly language. And even though it's much easier, right, we've been talking about how it's closer to English, this makes it a lot easier to work with, it's still not perfectly intuitive, and it can still be time consuming to write. So all of these reasons, this is part of why we're going to work with assembly language a little bit. You'll have 3 labs, possibly 2, but probably 3 labs on assembly language, and then we will spend a good portion of the class time on C language because, as you'll see, it is much more user-friendly. So it's important for you to become acquainted with assembly language and have an idea of how to use it, but we'll move on to C, which is much more user-friendly later on in the course. This time I have a snippet of C language here. This is a snippet of a C language code. And hopefully you'll see that it is even easier to read than assembly language. This right here, we have a counter that's easily recognizable. That's actually a full English word. There's no crazy abbreviation going on there. While is spelled out, so while this scenario happens, the code is going to execute these next couple lines. This says if, let me go up here, So this is declaring an integer. That's a little bit of an abbreviation there, but it's declaring counter as an integer, or that's going to be a number. And so we see this code is a little bit easier to read. There's fewer abbreviations and trying to remember what they are and things like that. And so instead of an assembler, we still have to convert C language into a unit that or into a code that the processing unit can use. So instead of an assembler, we use what's called a compiler to translate the C language to machine language, much like we use an assembler to essentially translate assembly language. So it's performing the same task. An assembler and compiler are performing very similar functions when it comes to translating the programming code into a machine code that the processing unit can easily read. So just like machine and assembly language, I put together a short pros and cons list for the C language. Again, a pro is many commands are in English, no crazy abbreviations, or fewer abbreviations rather. And I think on the assembly language, we said it was easy, it's easier to remember, easier to write. So C language is even easier to remember, and it should be even easier to write. And even easier again to modify and debug and find those errors. And because it's more intuitive, that also means you're less prone to making those errors. So that's part of why that we spend more course time on C language, is because it's a little bit more user-friendly than assembly. The cons to C language are that it's slightly slower to execute. Again, that's where the compiler comes into play. So we need a little bit of time for that translation to machine code to happen. And one of the biggest cons that you may wrestle with later on when we use C language is that syntax is extremely important. So everything has to be set up in a very specific format when you're using C language, so the commands are easier to remember and to use. But then C language has got some weird little quirks and things like that. Semicolons have to be in certain places. And there's some other important notations that you have to be in there, or spaces that can't be in there, that if they are, they'll create errors in your code. So syntax is very important when we're programming in the C language. So if you get into a situation where you think you have your code written out correctly and it's just not running, you're still getting error messages, I would encourage you to go back and look line by line and try to find any weird little spaces or things like that that could be going on. It might just be a syntax error. In the previous lecture, we talked about registers as being part of an architecture, both in microprocessors and microcontrollers. So when it comes to the assembly language, we use registers to temporarily store data. And there's typically a limited amount of registers, because if there's a smaller amount, it should be faster. That's a typical design principle. And usually we'll see 32 or 64 registers are available to us when we're programming. And again, these are just temporary memory locations that you can store things in for a short period of time. And there's other locations if you need to store data for a longer period of time. But we typically use registers when we're doing things like calculations to temporarily store numbers in until we add them or until we move them somewhere else. And there's usually a set number. So 32 or 64 is usually the number that you'll have available to you. And register files are usually built with SRAM. So I've added a little snippet down here on the side, just a quick refresher of what SRAM is. That's static random access memory, and the charge is maintained and it doesn't go away. So it doesn't require refreshing. It'll be there if the system is turned off or turned on. It's stored. But it's supposed to be a shorter path to the data. So again, this is not for long-term data. It's a quick path for data to be stored temporarily until it moves into a memory location, or until it's added or combined with something else and moved into a memory location. So what we'll find when we're programming in assembly language is that registers are often signaled by putting a $sign in front of the register number. So this example I have here, it looks like $4, but it is actually signaling register 4. So in some assembly languages that you come across, and it varies a little bit. Remember, we kind of talked with two combining a particular language with a computer architecture can result in a unique output. So this varies a little bit, and in the programming that we'll be doing, we don't represent our registers with dollars. But here, and you'll often see this, is that a register is represented with a $sign in front of the register number. Here's a list of registers that you can typically find in a unit. So I mentioned that you typically have 32 to 64 available to you, but some of those registers are reserved for specific purposes. And this is a good list that shows some of those specific purposes that can be assigned to a register. So some of them are already used. You'll see at the top we have register number 0, also known as the 0 register, super original. This register always holds the constant value of 0, so that value will not change. It's also important to note there are typically saved registers. So down here in this list, it happens to be register 16 to 23. Sometimes you'll see this alternate name. We have the $sign to indicate that it's a register, and then S to indicate saved, and the saved register number. So you can kind of use either one when you're programming the register number, or it may have an alternate name. It depends, again, on the system that you're using. But these registers are used to hold variables, any variables that you're using when you're programming. And then we have things like temporary registers. These can hold intermediate values during a larger computation. So if you need to hold something temporarily without saving it, you can temporarily hold it in one of these registers. And so I'm not going to cover everything in this list, but this is just to kind of give you an idea of not all registers are necessarily available to you, and some are for specific purposes. So we'll see when we get further into programming, you'll know specifically what registers you have available to use, but just bear that in mind. You may not always be able to use register 1 as a temporary holder for a value. You may have to start with register 6 or 7. So just bear that in mind, what registers you have available to use when we get into assembly programming. Something else to be aware of when we're talking about registers and programming are register flags. So some of these registers are set aside as specific flags. For example, we have an overflow flag. My highlighter. We have an overflow flag. So we just looked at adding two numbers and seeing that there could be an overflow. Sometimes that indicates an invalid number. So if there is an overflow, the overflow register would throw up a 1 or an active number. It would be turned on. So it would have the value of 1, and it would indicate that there is an invalid result if we see a value in this register. Or for example, if we end up with a negative number from our calculation, we would see a 1 in the sign flag register. So that would throw up a value of a 1 to indicate that the calculation is negative. If the result is 0, then we would see a 1 in the 0 flag register to indicate that the result of the calculation is 0. And if it's not 0, then you would just see a 0 in the 0 flag register. And if the number wasn't negative, then you would see a 0 in the sign flag. So much like the logic gates where numbers, we use 1s and 0s to represent off and on, the 1s and 0s represent these flags if these flags are off and on. So if a flag is active, it's turned on, there will be a value of 1 in that flag register. Another important one is the carry flag. So we talked about the overflow, and in conjunction with that is the carry flag. So if we perform a mathematical operation, usually addition or subtraction, and the result doesn't fit in the number of bits or bytes that we're working with, and we have one left over, then the carry flag will be activated. And you'll see in this lab that we do this week, you will be paying attention to the different registers and their flags. This addition example right here shows us how some of these flags are used. So we have two hexadecimal numbers. We're adding 80 in hexadecimal to 80 in hexadecimal, and our result ends up being 100 in hexadecimal. And looking at some of these flags, so the sign flag is 0 because the most significant bit is 0. So this is not a negative number. However, you'll notice that the carry flag is on because we've carried this one out over here, so that flag is going to get thrown. Then our overflow flag is also going to be thrown because these numbers that we're adding, it says they're both a negative, but the result is 0. So the overflow flag is thrown on that. There's also a 0 flag thrown because the result is 0, and the parity flag is thrown as 0 as well. So we can kind of see how all of these different registers, how the flags would be thrown based on the result. So we talked about registers, but we also have memory available to us. If you remember when we talked about architecture, we have both registers and memory typically. So memory is needed for more complex or lengthy programs. So if we want to temporarily store a value, or if we want to access it very quickly, the register is the best place for that. Unfortunately, we only have a limited number of registers, and again, their purpose is to pull values very quickly or to hold them for a short time. So if we needed to store something long term, or if we didn't need to access it as fast, or if we ran out of registers, we can store values in memory locations. So we talked about how we may note registers in programs, and memory is a little bit different. So memory is noted with an ampersand symbol, that's that little and symbol before the number. And then we typically have a 4-bit hexadecimal memory location. And our memory locations will usually start, our first available location is the number 200 in hexadecimal. It's very important to fill out all 4 bits. So if you need to, fill in the zeros on the left. And the highest, our largest number of memory location that we will have available to us will be the number 09FF in hexadecimal. And you'll notice, or you may notice, this little H on the end of these numbers. And that's important to write when you're recalling memory locations. So that H notes that this number is in hexadecimal. So we'll see some programming examples later on, but just note that when you're programming and you're storing values in memory locations and you're recalling memory locations, this is how you will write them. You'll put an ampersand, the 4-bit memory location, and then an H following after to note that it is a hexadecimal number. Very quickly, as we're programming in assembly, you'll realize that we need to load a number into a register. So these numbers are called integers. Most of you are probably familiar with that. An integer is just a whole number that is not a fraction. So 1, 2, 3, 4, 10, 125, 1506, and so on. Anything that's not a fraction, that's an integer. And when we're programming, we use integers very often to set register values. So at some point, you're going to have to load a value into a register. We may carry on and add one register to another register or increment a register by 1, but we usually have to load in an initial value. And so when we do that, we have to write integers in a specific way. So I'm going to cover 2 specific ways here. This kind of ties into what I was talking about. The computer architecture can be a modifier of the programming language that you're using for a total unique system. Again, just like a country can kind of modify the accent of a particular language. So there's 2 different ways that we can write integers. There's more, but 2 different ways that we'll cover that we typically write integers when we're programming in assembly language. So the first is that integers can be prefaced with a number sign, or maybe you're familiar with this as a hashtag symbol, and then we would end with an H. If they were a hexadecimal number, we would end with a B if they were in binary. And so you see here, I just have a few numbers. I have the number 03E5, that hexadecimal number, and then I have the number 1 in hexadecimal, which is of course the same in binary and decimal, actually, for just the number 1. So I have these written for a specific system. Now, the system that we will be using in this course this semester, we are going to preface our integers with just a 0 and an x. So you'll see the first example I have there, 0x5, that is just the integer 5 in decimal form. And then the second one there, 0x34, just 34 in decimal form. And so just be aware of this when you're programming in assembly language to preface your integers in this manner on the bottom here. And you'll see too when we get into composing our code that if you try the top method with this number sign and maybe the H on the end, it will flag it as incorrect. It'll say, hey, what's going on? This isn't how we write our integers in this with this particular architecture. And so you'll know, or you'll be reminded to just use this bottom format when you're programming for this course. As we work with assembly language, it's important to become familiar with a couple different terms. The first one is a mnemonic. The M is silent, so it's a mnemonic, and that just indicates what operation is being performed. So that could be synonymous with the word command. Essentially, it's going to tell you what's being done. And then we have operands. So that's the quantity. It could be a number or some sort of other variable that we're performing the operation on. And then within that, we have source operands and destination operands. So the source operand is the value that the operation is being performed on. And sometimes we have a destination operand, or we always have a destination operand, where the results that we get from our operation are stored to or where they're written to. And these operands can be a constant, so they can be a specific number. They can be stored in places, or they can be retrieved from a certain place. So instead of a number 5, you could use a number 5, that could be your operand, or you could have a register or a memory location as your operand that is pulling the value there. So we can store them in different places. Again, registers are good for small pieces of information and we can retrieve them very fast. Memory is good for storing larger pieces of information, but the retrieval is more slow from the memory. When we get into programming, you'll see 3 different program sections in the software most likely. So you should have a section.data. Essentially, it's almost like a command or a mnemonic, but it'll look like this, section.data. And so what that's doing is it's declaring the initial or constants that don't change when the program is run. So it's declaring all the initial information that you might need, and this information won't change as you go on through the program. The next one looks like section.bss, and this is where we declare our variables that we use. So if you're going to have a variable that's constantly changing, say you need a random number that you're going to be using, and that's always going to be changing, you can declare that as a variable. So you can declare the variable random number, and then you can keep changing that random number as you go on through the program. So this section is where we would declare all of our variables that we're using. And then we have the section text. So this is where the main part of our program is. And typically it'll look like this. It'll be underscore main with a colon after that. And that below this is where all of our main code for the program will be written. That's all the things that are changing, all of the commands that you're stepping through, anything that's not initial data that the program needs to run, or any variables that are going to be used should all be written under the main section.text program section. Now we'll move on to one of the most basic commands in assembly programming, and that is the move or moving command. So I mentioned just a second ago that often we need to move values into registers, or we need to move values between registers or between memory locations. Essentially, any time that you need to move a value around, either loading something into a location, changing its location, etc., we will be using the move command. So the mnemonic for that is just MOV. And you can see you can write it multiple ways. In this top example, it's all in lowercase. The bottom, it's all in uppercase. Writing your mnemonics in uppercase is a good practice just to keep them easily distinguished. Some compilers will only accept them as completely capitalized. It just kind of depends, just something to be aware of. Again, I think best practice is always to capitalize, but not saying that's always a must. So again, MOV is just our short mnemonic that we use to signal move. And then you'll see this specific format up here is we have a destination that we write first and then a little comma, and then we write the source. So what are destinations and sources? So your destination is the register or memory location that you're depositing information into. It's the destination. And the source is just where you're pulling that information from. Now, sometimes the source is a register, so you're moving a piece of information from one register to another, or sometimes the source is just the information itself. It's not in the system yet, and you have to load it in. So we put the information in directly, and we'll look at this example in a second that shows that. So we have a destination and a source. It's very important to remember that you format it as shown in this top line here, where the destination comes first, and then there is a comma and the source comes second. So it's very important that you don't swap these two, or if you make a mistake and swap them, pay attention to what's in your registers and you'll catch that mistake. So it's also important to note that both of these cannot be a memory location. So in our examples, we'll typically only be working with registers to keep things simple and to use the online composer that's easily accessible to everyone. But sometimes you'll be using memory locations if you're programming in assembly. And so when we move things, we can't move things from one memory location to another. We can move things from a register to a register. We can move things from a register to a memory location. We can move things from a memory location to a register, but we cannot move from a memory location to a memory location. So just a little caveat there. If you need to move something from one memory location to another, we would have to insert kind of an intermediate line and use a register as a buffer. Right, so you could move it from memory location A to register 1, and then move from register 1 to memory location B. So just a note, again, you will not have to move things to and from memory locations in your examples, but just something to be aware of. That's a caveat of this move command. Okay, let's move on to the actual example. So I have two here, and here you can see this first one. I have my move command set up right here, just MOV, and again it's capitalized because that's best practice. And so you'll see I'm following the order shown in the formatting right at the top here. And so according to that, my destination is going to be register B0. So when we use our coding online or our composer online, the registers are going to be in Bs. It'll be B0 through 31, I think. So that's how the registers are written here. So this example, I'm moving a number into the register B0. And I'm just moving the number 0 in there. So again, with integers and this particular composer, we preface them with a 0 and an X. And so you can even see I have a little comment here. With this line, I'm just moving the value of 0 into register B0. So why would we do this? Why would we put a value of 0 into a register? This is really good to do at the beginning of a program, because if you've stopped it in the middle or somebody else has stopped it in the middle, you might already have a value loaded in your register, and so that could affect the rest of your code. So typically it's good practice at the beginning of the code, or of course at other points as needed, to clear out. You're essentially clearing out the register. And so there's a couple different ways we can do that. There's actually a dedicated clear function. But one way to do that would be to move in the number 0. On this second line here, you'll see it's pretty similar. Just have the move command again. This time, my destination is going to be register B1, and I'm going to move in a value of 20. And so again, 20 is the source that I'm just directly inputting, and B1 is my destination. Now, what I can also do, or alternately do, is instead of this 0 times 20, this value of 20 here, I could write B2. This is another register. And so what that would do is move whatever the value of B2 was, it would copy it over into register B1. So registers B1 and B2 would then have the same value. So you can move things from a register to another register, or you can directly input values with the move command. We also have addition and subtraction commands. So I'm going to go over those one at a time. So much like the move command, we see this is formatted as destination first, source second. So I'm jumping ahead a little bit. Let me go back to the beginning. So the mnemonic for the add command is just ADD. This is pretty simple, add. And then of course we're going to list our destination first, a comma, and then our source second. So it's adding these two numbers together, adding your destination, adding your source, and it's storing them in the destination. So it's adding these two numbers together, and it's just going to store the result in whatever is on the left. So we talked before about how when we move things, we can't move things from a memory location to a memory location. We don't really have that restriction here with the add command. We can add two memory locations, two registers, a register and a memory location. It doesn't really matter. The only big thing to be aware of here is that whatever variable you put in on the left over here, that's where your answer is going to be. So you don't get to add A and B and store it in register C. You have to add A and B and store it in register B, or store it in register A. Your result has to be stored in one of the sources. So just something to keep in mind. Okay, so I have an example down here, an example. And these are the move commands that we just looked at. I copied over the same commands here where we put a value of 0 into register B0 and a value of 20 into register B1. And so now I'm going to add register B0 and B1. So I have ADD. This is my addition mnemonic. Pretty easy to remember. Again, all capitals, best practice. And I have B0 as my destination, and I have B1 as my source. So I'm adding these two numbers together, and try not to get confused. So this first number here kind of functions, this first number right here, or in this case, this B0, it's referred to as a destination, but it essentially functions as a source and a destination, right? It's part of being what's added, and it's the destination for the result. So I just want to reiterate that so we don't get confused by the language here. So I'm adding the contents of register B0 and B1, and I'm going to store the result in B0. Well, we can do this pretty easily. So we have 0 plus 20 is of course going to be 20, and then we'll store that result in B0. So the new value of B0 will be 20. And so essentially what we've done here is make registers B0 and B1 equal each other. And of course it doesn't always have to be that way. I'm just going over how it worked out in this specific example. Because we added 0 to a number, now the registers are both equal. Let's switch this up real quick and we'll see another potential outcome here. So instead of 0, I want to make register B0. Let's put 10 into there. I know that's kind of hard to see, but bear with me a little bit in our electronic marking here. So we'll load the value 10 into the register B0. Again, we're going to add our register B1 and B0. 10 plus 20 is of course 30. So now B0 is going to be equal to 30 and B1 is still equal to 20. It's unchanged, right? Because it's just the source, not the destination. Okay, subtraction works much the same way. Just again, we have to keep kind of our source and destinations straight. Let me switch to my highlighter here. So subtraction we represent with SUB. It's pretty easy to remember, SUB for subtraction. And again, we have what we refer to as a destination on the left, separated by a comma from the source on the right. So here formatting is a little bit more important, right? It doesn't necessarily, it doesn't matter which order you add two numbers in, but it definitely matters which order you subtract them in. So we have to make sure we get the right numbers plugged into our destination and source. And so this second line helps us remember what goes where. The destination functions as the first number in the subtraction equation, and the source functions as the second. And then, of course, they get stored in the destination. So let's put a couple numbers to this to help understand. So if I have this subtraction command, and in the destination, I'll load the number 7. Of course, this would be in a register. So let's say this register is equal to the value of 7. The source we'll say is equal to the value of 2. You know what, let's do this properly. So let's use B0 as a register, B1 as a register, and now over here I'll define them. So B1 will be equal, B0 will be equal to 7, and B1 will set to equal 2. I don't want to directly plug integers over here in this equation like I just had them because I don't want to confuse you. I would like to put them into registers first and then go off of those registers because it's best practice. So we've loaded these values into our registers. We've probably used a move command to move our 7 and 2 into place. And so we would have SUB B0, comma, B1. And so what we would really be saying is 7 minus 2, and of course that equals 5. And so that would be getting stored into the variable on the left, which is B0. So then B0 would no longer be 7. B0 would in fact change to the number 5. So that's where we would store the result. And that's just how we go through subtraction. It's pretty straightforward. Both of these don't have to be registers. Of course, your destination should be a register, but you'll see up here, look back up at where the addition is. The same rules apply here. Your source can be a register, a memory location, or intermediate. Intermediate is just an integer value. And so when we're subtracting, what we actually could have done is we could have plugged in a 2 directly. You write it out properly. And so we didn't have to plug our source number into a register necessarily. We would have been fine without it. Again, I just did it because I think it's good practice to do that. But the source can be an integer directly. Now, the variable on the left, of course, this B0, this needs to be a register or memory location so that you have somewhere to store the result. We have a few more basic commands in assembly language that are pretty standard. So the first one is CLR. And this command just clears the register or memory location. So I mentioned before there's a couple of different ways to clear a location. One of those ways was to move in the value of 0. A quicker, faster way is just the clear command, and then you would put the register right after that. So you could say clear B1. and it will wipe out any value that is in register B1. And again, this is best practice to do at the beginning of your program if it's been run before, and if it's really important that those registers start at 0. For instance, if you're using a register as a counter, you want to make sure that it's cleared out at the beginning of your program. Or you might need to clear it as a reset at the end of your program. So many different uses, but a clear command will wipe out any contents of a register or memory location. The next basic command is INC, and this just stands for increment, essentially, and it increments your value in your location by 1. So if you have a value of 6 stored in your register, it'll just add 1 and the new value will be 7. So we would put increment and then just simply your register. Increment B2, whatever value is in register B2 is going to go up by 1. And so typically when you increment, it always goes by 1. So whatever value is in that location, 1 gets added for every time you have this line of code. Similarly, there is a decrement command, DEC, and that just subtracts 1 from whatever value is in your register or memory location. So again, we could just put B2, and whatever B2 is equal, it will subtract 1. So if B2 equals 10, and we say decrement B2, it'll be equal to 9. So these are pretty straightforward. There's not really, you don't have to worry about commas or the order of things. You just put a register number or a memory location after these first 3 commands, and they'll be cleared, incremented, or decremented, of course, depending on which one you've used. The next basic command is the main command. So it's an underscore main and a colon. Essentially, all assembly programs start with this. You can declare some of your variables before you use this. You could clear a register before you use this, but you'll really want to put the bulk of your program, if not all of your program, and probably best practice if you're unsure, I would say put all of your program under this main command. This is really how you should start your program. Now, these last 2 they're not interchangeable, but they represent the same thing. So again, this is where the computer architecture comes in to modify the language. So it's unfortunate because it can be a little bit confusing, but sometimes you just have to go through a trial and error, or as you become more familiar with the architecture and how it modifies the language, you'll get used to knowing which one to use. So I just throw these 2 out there so that you're aware that sometimes the assembly language changes a little bit depending on the architecture, and you can look out for those differences and see how they might affect things. Okay, so after that explanation, let me get on to the actual mnemonics and commands. So the END mnemonic ends the program. And this is what we'll use when we are programming for this course. Pretty straightforward. We just use the end command. Nothing comes after it. It stands alone. We just put it at the very end to signal that it's the end. Not really a whole lot to say about it. Now, in some composers with certain architectures, the program is ended by NOP. And this just stands for no operation, and it ends the program. So this is an alternate command. In the past, we've used MSP430 launchpads. They're similar to Arduinos. It's just another little microcontroller. So if you use those with Code Composer, then you have to end your program with NOP. But again, just to reiterate, what we're using for this course, we will end it with END. I'll even highlight it. This is the one that we want to use, but again, just to be aware that sometimes there are alternatives. As you're writing codes is remembering what the code does. So in some cases it's obvious, but in some cases it helps to leave yourself a little note.
And so we can do that with semicolons. So down below, I've included a couple of snippets of a code, and you'll notice after the code, I have a semicolon and a comment afterwards. So a semicolon nullifies anything after it. So what that means is the computer will ignore anything on the line after a semicolon, and then it picks up on the next line. So the computer is reading that it's going to move this value into register 6. And you can see this is my comment, right? This kind of reminds me of what the line is doing. And so the computer isn't reading my comment, and it picks up reading this second line here. It just sees this command. And on the second line, I have another semicolon and a comment after. And this comment reminds me that I'm just adding the register 6 contents to the memory location 200 in hexadecimal. So as you're programming, you should be using comments to indicate what's going on, to remind yourself what's going on, and to show me that you understand what's going on.
This is just a snippet of an assembly language code to kind of get some command recognition. So we talked about how registers can be identified with a $ in front of them. In the cases that we're going to be using, it will just be the letter R in front of the number. So you'll be using R2 to represent register 2 if you haven't caught on to that already. So looking at this code, let's see what commands we can identify. We won't go through all of them, but we'll look at a few. So I'm seeing right here, this line right here, this is the move command. And what we're doing is we are moving, remember our source is on the right, destination is on the left. So we are taking the number 0 in hexadecimal and moving it into register 2. And you may note they're only using 2 bits here to represent locations. Best practice is to use at least 4, so this should be 4 zeros. But moving on to the next line, we see the clear command. What else can we see? We see a subtraction command down here. This should really only have one B. It should just be SUB. But so we're subtracting the hexadecimal number A from the location A. This would typically be a register or a memory location. Here we're incrementing register 2. So whatever's in register 2, we'll just be adding 1 to that number. Further down, we see we're decrementing, we're subtracting 1 from register 2. And so you can start to see different commands, and you'll start to recognize them and become more familiar with the setup of an assembly language program. So now that we've talked about some basic programming commands and principles, we're going to dive into logic gates, masking, and shifting registers. So typically this would be divided up into 2 classes. I think it's a little bit easier to separate them to talk about programming basics in one class and then getting into a little bit more details in the second. But because we're in an online weekly format, those are going to be combined into one lecture. So we can also use logic gates when we're programming in assembly. We talked about logic gates last week, some common ones and or XOR, NOR, right? We have a lot of different options. So we can actually use these gates when we're programming. So one of these applications is masking bits. And we'll get into the details of masking in just a second. But essentially, when you are masking bits, you can make any irrelevant bits, you can set them to a certain value so that they're filtered out. So for example, if we want to filter out everything except this last bit, this 2 right here, this is the only value that matters to us, we can apply an AND filter. We can AND this first number to the second. And with AND, you'll remember it says that there has to be a value in both registers for it to be valid. So if there's not, and there's not because this number here is all zeros, we're using this to kind of clear it out. By ANDing these 2 numbers together, we get a result that zeroes out all of the other places except this 2, which is the only significant bit to us. So we'll get into those details in just a second and look at that closer. But just to cover what else logic gates can do, we can also combine numbers. So if we need to combine, you'll notice this first number has bits in the most significant places. So it has 4 significant bits here, the most significant ones, and this has 4 significant bits in the lower nibble of data. So we can combine these two together by using an OR function, saying that if there is a value in either of these places, to add it in. And so this is combining these two numbers into one. So we can use the OR function to do that. Something else that we can do is we can use the NOR logic gate to invert bits. So saying whatever is in the 0 register location to go ahead and invert that, flip that around to the opposite number. And so we can use logic gates when we're programming to help us perform tasks. Much easier than it would be if we were to write. It would take multiple lines of code otherwise to perform these tasks. So now we'll just take a quick refresher of the different logic gates. So hopefully this looks familiar to you. I'm going to cover it real quick just because we'll be getting into a little bit more detail later with masking and shifting. So I want to make sure that we're understanding these gates and we're remembering what they're doing. So an AND gate is where the output is only true or valid if both inputs are valid. So the only way that an AND gate that you'll get an output is if both of your inputs are turned on, or if you have an input in both places. Then we have an OR gate that says there will be an output as long as there is a valid number in either input. There will be an output there. We also have an XOR gate or an exclusive OR gate that says the output will only be true if one or another input is true. If neither input is true or both inputs are true, we'll get 0 or false for our output. So only an output if there's only one input. Lastly, this is our fourth and final gate that we're going to review. I'm not going to review all of them, just the 4 that are most relevant right now. So we have our NOR gate, our not OR gate, where we have, this one only has 2 inputs, 1 output, and our output will only be true if neither input is true. So as long as we get zeros input for everything, we will get our output of 1. So we learned about logic gates, we reviewed logic gates, but why do they matter so much for assembly language? So what we can actually do is we can use assembly codes to perform these logic gate tasks in a much shorter way than it would take if we were to code these in some other way. So the first thing we're going to do, you'll notice instead of R's, we have our registers written in dollars. So your textbook, the assembly code and architecture that they're using a $sign to represent a register, and these are $S, so these are all saved registers. When we program in our code composer, which will be a separate video, or rather instructional video walkthrough, we'll be using R. So this would be R1 for register 1, R2 for register 2. So we're flip-flopping back and forth a little bit, but it's good to know the different representations possible for registers. So at any rate, you can see we have 2 source registers up here. We have source register 1 and we have source register 2, and these registers contain some data. So we have 8 different nibbles of data in here. And so down here we have different assembly codes that we can use. So this AND code right here is saying that we're going to AND the values in S2 or register 2 and in register 1, and we're going to store those over here in register 3. So I'm going to do that. I'm actually going to populate all the values for the table. Okay, here are the results of the logic gate operation. So we'll go through these one at a time, starting with the AND gate. So if we AND together, if we use AND logic on registers 1 and 2 and store the results in 3, here's what we get right in that first row under the results. So remember, in an AND operation, both inputs have to be positive or a 1 for a positive output. So 1 and 0 does not fulfill that, the output is 0. Same thing for the second row and the third row. This does fulfill the requirements. So both register 1 and register 2 have a value of 1 there. So that means the sum in register 3 will be 1. And then for 1 and 0, again on the left-hand side there, we see that does not fulfill the obligations of the logic gate, and so the result is a 0. So this first nibble here that we just went through is what happens when we do an AND gate operation on two registers. Going through the second, we have a 1 and 0 again. The result is 0. The second and third sets are 1 and 1, which fulfill the requirements of an AND gate. So we're going to put 1 and 1 down there, and that last one is a 1 and 0, and so that's 0. And so we would continue to populate the register in this manner, or rather this is the operation that's being done behind the scenes if you're using a programmer. But we would just continue to go through that by hand and use that logic for all of those. The next gate will be the OR gate that we're going to use, or the OR command, and we'll store that result in register 4. So just a reminder, for an OR gate, one value or the other has to be a 1, or it has to be on for the result to be 1, or both can be on. And so we can see here the first 4 nibbles in that top row are all populated with 1s. And so we know for the result to be a 1, at least one register has to have a 1. And so we can go through and we can look at each set individually. But really, all we need to do for those first 4 nibbles is look at that first register and see that those are all 1s. And because that fulfills the obligation already, we know the result is going to be entirely 1s or have an on value for those first 4 nibbles. Looking at that next set there, we have 0s in the top, but in the second register, all of those values are 1. And so we know the results will all be 1. And so anywhere in these registers where you see a 1, there's going to be a 1 as your result. So using the OR command is pretty simple when you are combining values in registers. Now, using XOR is an exclusive OR. So when we use this, this means that only one or another of the values can be positive or can have a value. It cannot be both. So in a typical OR gate, you can have one or the other or both. XOR is just one or the other. So here we have to be a little bit more careful. So we go through these 1 and 0, 1 and 0, we have a 1. Now we have a 1 and a 1. So because this is an exclusive OR, our result is a 0. So you have to be a little bit careful there. When both registers have a 1 as the value that you're XORing together, the result will be 0. So we're just going to look for anywhere that only one register has that value of 1, and that's where you'll get a result of 1. Otherwise, if both values are 0 or if both values are 1, your result will be 0. Okay, now we're moving on to the NOR gate or NOR operation, and NOR is essentially the opposite of OR, so it is not OR. So you would take the results from your OR gate and flip them. So here in this case it's very simple. Since we've already gone through an OR gate operation already, the not OR or NOR is just going to be the opposite of that. So you can see all we're essentially doing is flipping that. Remember, a NOT gate will flip the value of whatever the original gate is. So you see we have 1, 1, 1 in that first set of nibbles, or 4 1s. I think I missed one in there. So our result is going to be all zeros. That NOR gate is going to go in and flip that. Now you see where I've highlighted up in the OR gate, we have values of 0. So if we look up at the registers, of course, when you OR together 0 and 0, your result will be 0 because neither value is a 1. But that NOT flips it, and so we end up with a result of 1. And so I think the rest of these are pretty self-explanatory to go through the rest of that not or gate. And so this is just how we use our logic gates to populate, or rather to perform some sort of modification on register. So we can apply these logic gates as assembly codes to source registers, and these are what the results would look like and how those operations work. We can use these logic operations performed on our different registers to mask or control different outputs. So masking is an efficient way that we can separate our variables. So if there is a variable or a certain part of a variable that we do not want to use, we can mask it off. Just like masking off a section of the wall when you're painting, you are not painting on that portion of the wall. We can mask off a portion of a set of numbers and not use them. So we can use different logic gates as a filter so that only certain bits can pass through. So we can mask the unwanted bits to be either a 0 no matter what or a 1 no matter what, so that they don't affect the result of what we're trying to do.
So there's two different ways, or two typical ways to use a masking, or to mask bits. And the first way is to use an OR gate. So we're going to use an OR gate on this number right here. This is in binary form, again, to make things easier to see, but this could be in hexadecimal. So this number is 10010101. So let's say we want to mask on the higher nibble, or these first 4 most significant bits here. We always want these to be on. And this could be for a lot of different reasons. For this reason, we could say you have a series of 8 lights, and you always want the first 4 to be on. So maybe there you have 4 lights outside of your home and 4 lights inside. Maybe you want your outside lights to be on no matter what. No matter if there's motion detected or a sound or the time or anything like that, you always want those to be on. So before, we've kind of assigned some real situations, some real life situations to our logic gates. Trying to kind of do that here. It's a little bit harder in slide form versus classroom form, but we'll see what we can do. So you always want your 4 outside lights on. This first number here is the data that you're getting from your home security device. And so this data is what dictates the lights being on or off. Well, we always want the lights on, so the 4 outside lights on. So what we can do is we can mask them to always be on. And we can do that by using an OR gate and this second number over here. So if you'll recall, with an OR gate, if either or both input is true, then the output will be true. So you can see that by adding all ones here and ORing these together, this number is going to make these first 4 outputs, or lights in this case, they will always be true and they'll always be on, no matter what input your alarm system is giving. So we're using this OR gate and this second number here to mask these bits, to mask the first 4 bits, so that they're always true or they're always on, and then we're still retaining the data from the lower nibble of bits, which may be used for something else. So we may end up with the opposite situation. Maybe instead of masking certain bits to be on, maybe we want to mask them to be turned off. So we have the same number here. Maybe this time I only care about the 4 bits at the end, or the least significant bits. So what I can do, instead of an OR gate, I can use an AND gate, and this number down here, and this will turn off these other bits, these first 4 bits that I don't care about. So remember, with an AND gate, both inputs have to be positive, true, or 1 in order for the output to be 1. So by ANDing our first number with this second number and putting zeros here, we can guarantee but the output will never be 1, right? Whatever number is up here will always be combined with a 0, and so that will always give us an output of 0 down here. And so that is masking these bits. And you'll see that we fill in the rest with 1s, because if we originally have a 1, it's going to be ANDed together. We're going to get an output of 1. If it was a 0 to begin with, it will still be a 0. So we can use an AND gate coupled with the right number of 1s and 0s to mask off the bits we don't care about, these first 4 bits, and to keep the last 4 bits intact. So that's how we can use masking bits to pull certain data or certain numbers that we might need and temporarily discard the rest of a number. Next, we're going to talk about shifting bits or shifting a value. So again, it doesn't have to be in bits, but bits, for the sake of understanding the concept, makes it very easy to see the numbers, but this can be done in hexadecimal just as well. So shifting, what that does is it moves a register value to the left, so to speak, or to the right up to 31 bits. So it's essentially acting as a divider or a multiplier. We're adding numbers either to the end of the value, or we're adding numbers to the beginning of the value to kind of shift it around back and forth. And so based on our place value notation, as you know, when we shift a number's place back and forth, that changes the value. Just like if we had the number 1 and we shifted it to the left and we added a 0 afterwards, in decimal that would be a 10. If we shifted it to the left 2 spaces and added zeros after that, that would make it 100. So we would be multiplying that number. Similarly, if we shifted the number 1 to the right and added a decimal in front of it, then that would be 0.1, or we would be dividing that number. So shifting can be a divider or a multiplier, and we have 4 different shifting options. So we can do what's called shifting logical left. And so however many spaces you shift the number, we would fill the empty spaces on the right with zeros. We can shift logical right, which is where we shift the number to the right and we fill the empty spaces on the left with zeros. We can shift arithmetic left, which moves the number and it fills any empty spaces on the right with zeros. So you'll see that shifting arithmetic left and shifting logical left are essentially the same thing. But then we have shift arithmetic right, and this one is kind of unique. Because what this does is any spaces on the left are not filled with zeros, but they're filled with the most significant bit. So whatever the most significant bit is, it can be a 1 or a 0, but it fills those empty spaces. Now we're going to look at a couple examples of how we can use shifting to alter a number. So the first thing we're going to do is look at shifting logical left. That's this first assembly code line right here. And so you'll see what we're going to do is we're going to shift what's in register 1, which is up here at the top. We're going to shift it to the left by 4 bits. And we're going to store that result in register 0, which is right over here. So everything is going to shift to the left. So this is actually going to disappear. It's gone, that first nibble. And then everything else is going to shift down left by 1 place. And so you'll see we have a spot at the end here that there's no number to fill it with. So based on the laws of shift logical left, we fill this empty space with zeros. And so we have a different number, right? By shifting everything to the left, we've essentially multiplied the number. But depending on how many significant spaces you have, your most significant bits may drop off. All right, so looking at our next one, we have a shift logical right. So this is pretty intuitive this time. Instead of shifting to the left, we're going to shift to the right. So over here, still working with register 1, we're going to shift to the right 4 bits again, and we're going to store the result in register 2. So looking over here in register 2, shifting this number to the right. This goes over 1 space, over right by 1 space, or 4 bits, right? Over 4 bits, 4 bits over 4 bits, 4 bits, whoops, a little farther, 4 bits, and then you see this one, this last nibble of data has nowhere to go. It just kind of drops off, and we have this empty space all the way on the left. So according to shift logical right, we just fill this in with zeros. And then as I mentioned before, shift arithmetic left is essentially the same thing, or it's similar to shifting logical left. You're just filling the empty spaces with zeros. So let me do that. So this is just getting shifted. I'm sorry, I went out of order. So first we have shift arithmetic right is our next assembly code. These are flip-flopped a little bit. So we're looking at shift arithmetic right. So what we do is everything goes to the right by 4 bits again. So we'll just draw lines to where everything goes. It's all going to the right. And then this last nibble doesn't have a place to go, so it's gone. And the thing that we do different when we shift arithmetic instead of shift logical is that we fill in the empty spaces with the most significant bit. So here we see the most significant bit is a 1. So that means that all these spaces on the left, these 4 bits, are going to be a 1 as well, because we're shifting arithmetic right. All right, now we're on to shift arithmetic left. This is our last assembly code all the way on the end here. And so shifting arithmetic left, you'll notice these numbers down here in this entire bottom row actually match this top row. That's because shifting logical left and arithmetic left do the same thing. We're shifting the number to the left by however many bits we call for, and we're just filling the empty spaces with zeros. So there's really no difference between those two commands. But when you're shifting to the right, if it's logical, you fill with zeros. If it's arithmetic, you'll fill with the most significant bit. Okay, we've covered a lot of different topics for programming, some different languages, assembly language commands, how we can use masking and shifting to help us program. So now we have our final concept, which is flowcharting. So this is not a unique concept to programming, but it is a great tool to have and to use, and you'll be using it in Lab 1. So we can use flowcharts to help create clear program steps to make our programming easier. Sometimes it's hard to figure out where to start in a program or what comes next. How do I get a program to perform a specific function? And so flowcharting can help us or help our minds step through the process. So when you're flowcharting, it's important to note a couple different symbols because different symbols or different shapes are used for different things. So an oval will be used at the ends and the beginnings of your flowchart, and it signifies the start or stop of a program. A rectangular box we use to indicate a task or a step that's being performed. And then you'll see we have a diamond here. If there's a decision, a question, if you're deciding between 2 options in your code or multiple options in your code, there's a decision or a branch to be made. You'll use the diamond to represent that. And then data, any data that's being processed is represented with a trapezoid. So as you're kind of laying out a flowchart for your program, we use these shapes to help indicate what's going on. So here's a flowchart for a common task to help us understand how flowcharts work. You may already be familiar with flowcharts, which is great. And if you're not, this example will hopefully be helpful. So remember, we start with an oval. So this is our start of baking a cake. So the first step, our task, remember we use rectangles to represent tasks or regular steps, would be to gather ingredients. So that's the first thing we're going to do. Next, we might turn on the oven. We're going to mix the ingredients together, and then we have a decision. So our decision, which is represented with a diamond, is the batter mixed without chunks of flour in it? Is it completely mixed? And if it's not, we're going to circle back. So we're going to point back to this task and write our decision here. What's our potential result? So if it's not fully mixed, we're going to mix some more. If it is fully mixed, it's cut off a little bit, but there's a yes arrow here. Our arrow is going to point us to the next step. So next we're going to grease the pan, we're going to pour the batter into the pan, and then we're going to see if the oven's preheated. So here's our options. So decision, again, in a diamond. Options written down by different exits. So each point of the diamond should be a decision option. If the oven's not preheated, we're going to wait, right? And we're going to keep asking ourselves, is it preheated yet? Is it preheated yet? Almost subconsciously, right? Until it is preheated. And then we're going to follow this branch down. So then we're going to put the pan in the oven and we're going to wait 20 minutes. If you wanted to get super detailed, you could probably split this out into 2 tasks, right? You could say place pan in the oven and then go forward and then wait 20 minutes. But this is just kind of a simple flow chart. So we're going to place the pan in the oven and wait 20 minutes. And then you'll notice I've done something a little bit unique that I don't necessarily recommend, but I've just used this little circle with a number in it to represent the connectivity of the flowchart because I've had to spread it across 2 sides. You typically won't need this. You should be able to fit everything on a piece of paper. So after it goes in the oven, you're going to check the cake with a toothpick. And is the toothpick clean? So if you're not familiar with baking, a toothpick should come out clean out of a cake to signify that it's cooked. So our options are no and yes. If the toothpick's not clean, we wait a couple minutes. We kind of we do this loop here until we can move forward. And so on and so on. So when your cake is finally done, we frost the cake and then we end, right? We have a fully complete cake. We represent that with an oval. So this flow chart represents the steps in making a cake. I want you to do the same as you program. I think it's good practice and it helps kind of sort out the steps when you're first learning how to program. And so you're going to do that for Lab 1, which I will detail a little bit more later on in that separate lecture, but you're going to use a flowchart to help you step through the different pieces. And so if you need to move a value into a register, add it to another number, and move that result, you should be writing down each step in your flowchart. And so as you go through your program, you can kind of check each step off. You can see if you need any loops or what the next step is or anything like that. So flowcharts are great for staying organized and programming in a very organized and simplified manner. So in the previous 2 weeks, you've had homework assignments. For the next couple weeks, or several weeks rather, we're going to have lab reports that are due. And you can do these a couple different ways. So I'm going to, of course, upload the lab report to Blackboard. You can print out this report, fill it out by hand, and scan it back in if you wish. If that's the best way you work, that's perfectly fine. There is an app called Tiny Scanner. There's a couple different apps that you can download. I use one called Tiny Scanner on my phone, so I can actually, it snaps a really clear picture of the paper that you're working on and kind of filters out all the unnecessary stuff and creates a nice little PDF file for you. If you don't have a scanner, that's a really good one to use, or whatever works for you. If you have a scanner, then that's even better. So you have that as an option, or you can also just fill out the lab reports in Word and submit them that way. That's fine. When you are filling out your labs, you're going to copy the programs that you wrote into the lab. So you'll be writing programs the next several weeks, and I need to see the programs that you're writing. So make sure that you're copying those into your lab, either down by hand or doing a copy and paste into your lab report. And then you'll add comments to the programs to explain each step of your work. So this is very important. So as important as writing the program is, it is also just as important that you add comments noting what each line of the program is doing.
In a separate video, I'll be reviewing an example of programming in assembly using Code Composer, but I do want to quickly review your Lab 1 assignment and report. So this is what the top part of Lab 1 will look like, and here's your objective or your assignment. You will be adding the hexadecimal value 0A3F from a memory location. I don't care what memory location that is, but you will be moving that into a memory location, and then you'll be adding that to a second hexadecimal value that is stored in a register. So you're going to store this value in a memory location, store the second value in a register, and add those together with the result stored in the memory location. Then you're going to subtract 1 from the result that you got, and if you think about it, there's a couple different commands you could do to subtract 1, and then you're just going to move that result into another register and move that result into another memory location as well. So that's the code that you'll be writing. And the first thing that you're going to do is you're going to draw a flow chart. So break down the steps that I've given you think about it in terms of different lines of code. What lines of code would you need to perform each task? What order would they go in? So you're going to want to draw a flow chart for that. And you can print this out again and draw the flow chart and scan it back in, or Microsoft Word actually has flow chart symbols that you can use if you prefer to do it all digitally. After you write a flowchart, the second thing you're going to do is actually write your program and go ahead and debug and build it. So once you arrive at a program that works, you're going to copy it into the table that I've given you. If you're writing this out by hand, go ahead and copy it into the table I've provided. If you're doing this all in a digital format, you're not printing anything out, you can delete the little table box I've provided to give you space to paste in your code. So whatever program you end up with, go ahead and paste it in here. And the third step is going to be, as you're stepping through the program, pay attention to those status registers. And you should see that in the separate video I've made for the Code Composer examples. So look at your status registers and see if any of them are flagged with a 1, if they have a flagged bit active, and note what happened. Why are they flagged as a 1? What step did that happen? And which status register changed? Also, I don't have it listed here, but the fourth question in your lab will be to write a short summary of any observations that you made throughout the lab and any concepts that we use. So what course concepts did you use in programming or flowcharting or anything like that? What course concepts did you use for this lab? And write a short summary of those and any other observations that you've made.